My name is Sliman Mitesh. I am a research assistant at the University of Sherbrooke. My co-authors are Mohamed Bouabidi, he's a PhD candidate, and the Professor Radwan Masmoudi, which is here. My presentation will contain an introduction, numerical modeling. Excuse me, the title of my presentation is Numerical Design Optimization of a New Hybrid Utility Pole. My presentation will contain an introduction, numerical modeling, results and discussions, and the conclusions. A utility pole is generally a vertical structure used to provide support for public utilities and services such as electricity lines, telecommunication cables, antennas, signal panels, or as support for a light. The US market for distribution poles is approximately $9 billion a year. It is estimated that about 3.6 million distribution poles, mostly wood, must be replaced each year. About 2 million new poles are added annually. The current US capacity for manufacturing composite poles is approximately 20,000 poles a year. The existing problems with the poles made of traditional materials like wood, steel, or concrete, according to the North American Wood Pole Council, the main reason for removing wooden poles is decay. Steel poles are relatively expensive, and can corrode when exposed to the natural elements. Concrete poles are heavy and are prone to degradation when exposed to the environmental aggression. Composite utility poles have gained wide acceptance in the utility market due to their high strength to weight ratio. They are corrosion resistant and their durability. However, they still have limitations such as susceptibility to buckling due to their thin wall thickness, and large deflections due to low stiffness properties. So how can FRP poles be improved? Alternative materials and design should be considered to have stronger and more durable poles. Hybrid poles can take advantage of the benefits of each material used. So the objective of this research paper is to study the feasibility of such hybrid structures. So several models were developed to showcase the performance of hybrid poles. Models were used to design tool for experimental phase. Proposed hybrid pole cross-section is constituted by an FRP shell, a steel tube, and a concrete core. The outer FRP shell provides protection and enhances the strength of the pole. The concrete core provides stiffness, and the inner steel tube enhances the overall flexural performance. We consider length of the poles is about 4 meters, 12 feet, 2 configurations with different taper ratios. For each configuration, the steel inner tube diameter was 50 millimeters and 70 millimeters. The figure on the right shows the four configuration of the poles. A new test setup was designed and built according to the STM and ANSI standards. This fixture provides practically a way to test all types of poles. This test setup is constituted by two supports, and the load is applied vertically, so we can measure the displacement and the force. But we will be interested by the cantilever displacement at the end of the pole, which is the deflection, the end, the top deflection of the pole. So numerical modeling steps are geometry definition, material models, loading and boundary conditions, elements group, connections and failure criteria, meshing, running the model and get results. So orthotropic material was chosen for the GFRP. The mechanical properties were obtained from previously tested specimens. 35 megapascal grade concrete was introduced in the data-fitted concrete model of the Adina software. And the steel was modeled as a bilinear material with 2010 gigapascal Young modulus, 0.3 Poisson ratio, and 460 megapascal yield stress. For the model studied, boundary conditions were set on the bottom supports to simulate a fixed connection. Load was applied to the top support. And to transfer the loads and the efforts between the different elements, glue mesh was used for each different element that is in contact with other elements. FRP layer was simulated using shell elements on the outer layer of the concrete hollow and tapered cylinder, and steel tube was simulated in the same manner of that of the GFRP layer. Failure of the GFRP concrete. All four models studied had similar failure location of each material. The concrete layer failed mostly in area near the base, both in compression and tension, and the FRP layer failed in the compression zone, mostly in the mid-span area. This figure presents typical load deflection curves. So a bilinear behavior was observed. First linear aspect of the curve was before the cracking of the concrete layer, and second linear phase after the initial cracking of the concrete. For the same configuration, deflection values are lower using a tube of 70 millimeter diameter, so using less concrete, than using steel tube of 50 millimeter, so using more concrete. This figure compares 5 models for the same configuration with 70 millimeter in diameter steel tube, varying the thickness of the FRP outer tube from 3 millimeter to 7 millimeter with 1 millimeter incrementation. The behavior of deflection is almost similar for loads under this value, 1,750 Newton, corresponding to the initial concrete cracking load. But at failure, 3 millimeter tube thickness deflected to almost 50 millimeters, while 7 millimeter tube deflected to almost 23 millimeters. This represents 50% reduction in the top deflection of the pole. So the following conclusions can be drawn. Failure occurred in high stress concentration areas. The concrete failed mostly in near the base, both in compression and tension zones. The FRP layer failed in the compression zone, mostly in mid-span area. Bilinear deflection behavior was observed. Opting for larger diameter steel inner tube helped both in reducing the volume of concrete, thus using less material, while providing more stiffness that led to lower deflection of the poles. For the same pole configuration, with incremental variation of the FRP thickness values from 3 millimeters to 7 millimeters up to the initial concrete cracking load, no significant variation of the pole top deflection was observed. However, at failure, increased the FRP thickness from 3 millimeter to 7 millimeters, decreased the ultimate tip deflection by 50%. We can say that new hybrid utility poles have the potential to be an interesting alternative solution to the conventional poles, as they can provide better mechanical performance. The authors would like to acknowledge the following: the National Science and Engineering Research Council of Canada for its financial support, INSERC, the Composite Structures and Material Research Group headed by the Professor Radwan Masmoudi, which is with us, the technical staff of the Department of Civil Engineering and Construction of the University of Sherbrooke. Thank you very much.